Yeah, so now we have by Andrew Harder, now we have a title. Yeah.
Okay, well, thank you for inviting me to speak here. So I mean, if W, or let's not say W, let's say Z and Z check are mere Clavier varieties, let's say mere projective Clavier varieties, smooth manifolds, then, I mean, one thing you learned very early on, we expect that HPQ of Z is equal to HD minus PQ of ZB. Okay, so this is, you know, a very basic expectation of just about every form of mirror symmetry that I know of. And so the question that you want to answer is, what happens when Z and Z check are not projective, when they're sort of log Clavier out? So what happens when, say, Z and Z check are no longer projective, but are still log Clavier out? Okay, so that's essentially the premise of the talk. Okay, so let's make so what are HPQ of Z? So these are graded pieces of the Hodge filtration on cohomology of Z and Z check. So maybe we can try to do the same thing for Z and Z check when they're no longer projective. So let's use maybe different notation for this. Let's say call them U and Q check, just to sort of distinguish notationally projective and non-projective things. So we can define the same thing. So let's make a guess.
So weight filtration, yeah, those three numbers, yeah.
Yeah, well, I'm going to look at the Hodge filtration first of all.
Okay, yeah.
So the first guess is that the graded pieces of the Hodge filtration on H star U and H star U check obey the same relations. And just to be precise what this is, so I mean, of course, any quasi-projective variety has or any algebraic variety has a canonical mixed Hodge structure on this cohomology. And so in this case, what we do to actually obtain these numbers, so precisely, so let, how do I say this? So let's let U bar be a compactification, be a smooth compactification of U, this is smooth compactification such that U bar minus U, we'll call D, is normal crossings. Then we'll let HPQ of U be this the dimension HQ, so dim HQ, say U bar omega D U bar log D. So this is the pth graded piece of this is the HPQ part of the mix of the Hodge filtration on cohomology of U. So then the precise conjecture of this guess here is that so a precise guess is that HPQ of U is equal to HD minus PQ of U check. Okay, where D is equal to the dimension of U is equal to the dimension of U check. Okay, so I mean you can check this. Let's just give a basic example.
So things are no longer symmetric in Q and P?
Yeah, exactly. It's sort of a weird thing, but it, you know, sometimes when you say this relationship, you know, for compact Clavials, you don't really need to care which is P and which is Q. You can sort of switch things around. But you have to be precise here, which is something I learned while doing this. So a basic example is that, so let's take C star to the D. So this is expected to be mirror to itself. And so what are these HPQ invariants of C star to the D? So HP0 of C star to the D is equal to D choose P. And HPQ not equal to 0 of C star to the D is equal to 0. Okay, so then what do we have? So we have HPQ of C, well, let's say HP0 of C star to the D is equal to D choose P, which is equal to D choose D minus P, which is equal to H D minus P0 of C star to the D. Okay, so there's one. So that's sort of the one piece of this. You can sort of complete the computation by saying, so HPQ not equal to 0 of C star to the D is equal to 0, is equal to 0, is equal to H D minus P Q not equal to 0 of C star to the D. Okay, so you see you got sort of the correct symmetry for C star to the D. Great.
Yeah, one quibble. You should think of a different notation, not call them HPQs.
Yeah, okay, yeah.
Because
No, I completely agree with this. Yeah. That being said, this is consistent with the other notation that you sort of
yeah.
I
have IPQs.
Yeah, I mean, notation is terrible. I apologize for any of it in this entire talk. It's probably going to be bad. Okay, great. So yeah, as Maxime suggested, I mean, there is also a weight filtration on this cohomology. So once U or U and U check are no longer compact, if U and U check are non-compact, cohomology admits a second filtration. So H star admits a weight filtration. So the question you can ask then is, what role does this weight filtration play in mirror symmetry? So
And also this filtration by different cohomology.
yeah.
It's still-
So we have 4 filtrations here.
Yeah.
We have a weight filtration. We have a 3 filtrations for now. I'll introduce another in a second. But we have 3 filtrations.
But numbers, I think, depends on 4 parameters, yeah? Because you have individual cohomology, and it has mixed sort structure.
Yes.
No, 3 parameters.
No,
3
parameters.
But I'll introduce the 4th.
3 parameters, okay, yeah.
Yeah, so that's kind of an interesting thing. Like, so the question is, what happens to the weight filtration? To the weight filtration. Under mirror symmetry.
So just to sanity check this, sum of this HPQ is equal to total rank of cohomology. Yeah?
Question mark. Okay. Okay, so just to think about how maybe. Okay, so what could it possibly correspond to? I mean, a priori, we don't really need it to correspond to anything, but sort of what could it possibly correspond to? So the question is, how does one compute the weight filtration? So the weight filtration is computed using compactification. So in the case, so I chose above a compactification of U to U bar, so that the complement is some normal crossings divisor D. Say U bar. And so it depends on sort of the geometry of D. So D is the union of divisors D1, so di, I equals 1 to k. So yeah, so this is how this is computed. So what do such divisors correspond to under mirror symmetry? So, I mean, I guess if you look at sort of, you know, an SYZ type picture of this, the divisors di, these correspond under mirror symmetry to functions on the mirror. So in this case, you check. Okay? So that's the first maybe fact here. I mean, yeah. Second, maybe 1. 2, the weight filtration doesn't depend on choice of compactification. On choice, we just need to know that such a compactification exists of U bar. So this should be, so the weight filtration under mirror symmetry should correspond to something that doesn't depend on a choice of functions.
So how did you get this U check?
U check?
Yeah.
Oh, this is the mirror.
It's mysterious mirrors.
Yeah. I'm not explaining how I get a mirror
that's
here.
what I-
Yeah.
Yeah, you can do this
Not well
with,
defined. Yeah.
this is not something that I'm talking about today, but like you can use SYZ
This way.
type constructions to do this. I think that's.
But you are assuming we use a caveat here, right?
Yeah, I'm assuming you use a log caveat. Yes. Yeah,
No,
log
no.
caveat is important. Or
You buy a log caveat, we use a caveat.
yeah, sure.
So I have one more question. I don't know, means what are means usually log caveats are non-compact, no?
Yes.
So why he is assuming when they are non-compact? They are always
Non-compact.
Yeah, always non-compact kind of. Is there any
No,
example?
because it's for compact we have this started with compact stories.
Yes, but when log caveat is non-compact.
Yes,
Why
yes.
this is the assumption?
No, it's not assumption. I know it's kind of generalization.
Yeah, he's
log-
asking the same question for
Yeah.
non-compact caveat.
Yeah.
A long caveat could have an empty divisor.
Yes.
Okay, we have to divide it,
Yeah, so it includes
It's
the
a set,
six.
sorry.
Okay.
It does this with maximum.
So maybe this is like an implication. So filtration W bullet corresponds to something that doesn't depend on choice of a bunch of functions. Okay, great. So this is justification for something that I'm going to do that maybe isn't super, you know, I mean, it's well defined, but I don't know why I'm doing it.
Yeah, but the way you stated it, it's a bit misleading because the weight filtration does not depend on the choice of the compactification, but depends on the fact that compactifications exist. The same way,
But this fact is
the filtration on the other side will not depend on the choice of functions, but it will depend on the fact that functions exist.
Yes. Yeah, that's true.
So
So I'm going to make a guess as to what this is going to correspond to, which I'll admit right now may not be actually correct. But it works in examples. I'll explain how this works in examples and how it sort of interacts with different things. Okay?
So as he said, means when he says so functions exist. Did you prove it? Means,
No, this is some part of mirror symmetry that he's assuming as a black box.
Okay.
I mean, we
Yeah, yeah.
know that
Exactly.
divisors contribute
Yeah.
potentials. And
So I'm just sort of saying some things that should be, you know, motivational for what I'm going to say next. So we can define the following thing. So what's a map on a variety that doesn't depend on, that sort of is intrinsic to the variety? Well, there's always a map. So there's always a function. Morphism. Going from U check to spec of C of U check. Okay. So this is the only function that I can cook up that is sort of intrinsic to the variety. Maybe there's others that I don't know, but this is one that definitely is intrinsic. And so what I want to do is I want to use this map to build some sort of filtration on cohomology. So how can we use this? Let's build the filtration on cohomology. So anytime you have a map, you have, well, at least 2 filtrations on your cohomology coming from this map. I'm going to choose one for practical reasons. So associated to such a map, let's call this just F. I don't know.
Is that identity map?
No.
If it's the identity if it's affine.
But fiber could be projected. It's
Yeah.
like, yeah.
Yes,
It's
exactly.
definition.
Yes.
But let me just point out that there is one more canonical map, which is the Stein factorization of this one.
Yeah. Okay. So, yeah.
So of course,
In the cases that I've looked at,
we have to
the
make a
Stein
choice.
factorization doesn't actually
Do anything.
Yeah, exactly. So maybe that could be involved in sort of a better definition, but sort of, yeah, that's definitely true. Okay, so let's see. So associated to this is a perverse Leray filtration on cohomology, or the perverse.
You assume F is proper map? Or?
Well, F is automatically proper.
No.
Definition is always.
No?
Well, oh yeah,
I
it's
don't
quasi
think
affine, you mean?
I don't know. It could be something. You can remove maybe some. Yeah.
Yeah.
Who
So
knows, yeah.
there's some issues in this. I mean, I'm not claiming this is perfect. Okay, so you get a filtration on cohomology. So how does this work? Well, we have that the hypercohomology on, let's say, U check
Subjective.
is equal to, let's just call this U. For the affinization, this is equal to, for cohomology on U of push forward Q. And so, I mean, we can always take perverse truncations of this complex. So this is complex of constructible sheaves. And so the perverse truncations which I'll call tau e here, must be equal to n of this complex, induce a filtration on H star U check. Filtration.
So, do you mean the spectral sequences degenerate? Or?
No, I'm not making inclusions with
So
anything
just
degenerate.
have
It
subcomplexes.
teaches the limiting filtration in the spectral
Yeah.
sequence.
Yeah, okay.
Yeah. On H star of U check. Okay, so that's my. This is called the perverse Leray filtration. Okay, so my claim is roughly that the perverse Leray filtration on cohomology corresponds to the weight filtration under mirror symmetry. So maybe I'll just give a secondary characterization of this, which is really useful for computations. And so this is a result of
So this filtration is just on a fiber part of the, not on a.
What do you mean?
No, it's on the total cohomology.
It's,
Yeah, but something like
It's-
fiber truncation on this fiber, right? On the,
yeah, somehow it has something to do with like the support of
Well, that, if F is isomorphism, it still has an optical filtration.
in a sense, yeah. I mean, so you get a trivial well, yeah. There's a non-trivial filtration. Maybe I'll give the secondary
Okay,
characterization,
yeah,
and it'll be more clear what this is. So, according to Di Cataldo and Migliorini, little d. The perverse Leray filtration is equivalent to a to the flag filtration for a general flag. And I'll explain what this is. Okay, so what is this?
Maybe they use a proper map. No.
Possibly. I don't think
No,
so.
I don't think they have it in the theory.
Oh, just any map from any
Yeah.
smooth variety to any.
Any quasi-projective variety, any, yeah.
Ah,
Yeah.
so it's very so general.
it's very
Yeah,
general.
it's general. Okay,
So, I mean, to affine target,
Yeah, to-
that's the only condition there.
let's see. So let's write this down here. So the flag filtration it goes as follows. So let's let a map from x to y be this is just a morphism. So let's assume maybe y is affine. I mean, I don't think this is completely necessary, but I mean, it's true in our case, so why not say it?
I think it's actually a hypothesis in that
Okay,
theory.
sure. And let's let y, let's see, dim y be contained in y, dim y minus 1 containing to y, y0 equal to y, be a flag of subvarieties in y. Let's see, of dimension, so that dim yi is equal to codimension I, right? So that this is true, so this is a flag, let's see, chosen generically. And so what this means, or what you can take this to mean, is that you take an embedding of y into projective space, and then you take a bunch of generic hyperplanes and start intersecting y with these generic hyperplanes to build this flag. Okay, then we're going to define this flag filtration, or what's actually the same as the perverse Fourier filtration. So then define, just to give a precise definition of what this perverse Fourier filtration is. Sorry, I forgot. Let's let xi, this is going to be the preimage of yi in x. Okay, so we also get sort of a flag of subvarieties on x just by taking the preimages of these things. Then we define P, and this is, I think, not quite the same. This is up to shift the same thing as Di Cataldo and Migliorini, but I think I changed things a little bit. Hn x to be the kernel Hn x Hn x I. Yeah. So sorry if this is not very visible. So this is like kernels of restrictions to different pieces in this filtration. Okay, so for instance, if you take a if this is one-dimensional essentially, you're going to look at restrictions to fibers of this map. I mean, that'll sort of be what determines your flag filtration. Or more, maybe I'll give another example, which is that if you check is affine, then the graded pieces of this flag filtration, which is the same as perverse Fourier filtration, are as follows. So U being affine means this maps the identity. So then GRP JH N B, this is equal to 0, J is not equal to N, and HDN, check if J is equal to N. Okay, so I mean it's fairly trivial. Okay, so what is the conjecture? So the optimistic conjecture that I'm going to make, the vague optimistic conjecture, is that if U and V are are mirror, and as Tony pointed out, I'm sort of misusing the word log Calabi-Yau here, but I'm going to say it anyway. Then the perverse filtration on U corresponds to the weight filtration, so H star of U. On H star of V of check. Okay, so that's my vague conjecture. Let's state something more precise now. Let's go back to the central.
That's including a pretty strong statement that if the weight filtration is non-trivial, then that ring has to be non-zero, basically.
Yeah.
Okay.
But that, you know, that's not a strong statement because that's somehow pre-built in the mirror symmetry. As he said, the SYZ construction and the counting of mass within these two disks tells you that every boundary component gives you a function. So you know that's going to happen.
Yeah, it might be possible that this turns out to be not quite this map that I've chosen, but in the examples I look at, it's okay. Okay, so let's make a definition to make a precise conjecture. So let's let U be a, say, quasi-projective variety, say smooth. Then define, let's define, I guess, something like, maybe call this something like the perverse mixed H polynomial or something like that. U, V, T, W, to be, let's write it this way because it's easier. The sum of all P, Q, R, and S of the dimension of the graded piece of the Hodge filtration. So P, graded piece of the weight filtration. Q plus S, graded piece of the perverse filtration. So the perverse filtration is being taken with respect to the affinization map. R plus S, and then H to the S, U, times, so I need the variables to be involved, U to the P, Q to the, V to the Q, T to the S, and W to the R. Okay, so this is a polynomial that keeps track of the degree filtration, the weight filtration, the Hodge filtration, and the perverse Laurier filtration associated to the affinization. Okay, so this is my definition, and so the precise conjecture doesn't go further. So precise is that, when did I start? How much time do I have?
About 20.
Okay, so I have about half an hour or so. Is that, I mean, under the same assumptions, U and U check are mirror dual, then H U of U to the -1, T to the -2, and there's some sort of inversion going on here, which sort of corresponds to switching Hodge numbers in sort of a more standard way. W, T, V, T to the D, U to the D. D is the dimension of U and U check, is equal to H, U check, U, V, T, W. Okay, so I'm switching V and W, and I'm doing something else here that messes around with these guys, but I'm sort of making up for it by multiplying it. Okay. Okay. So let's just do the most basic example that I mentioned earlier. C star to the n. Great. So I already have this. So let's redo it. So you can compute that the perverse mixed H polynomial of C star to the n is as follows. So H C star, let's say D actually, of U, V, T, W. This is equal to U, V, T plus W to the D. Okay, you can just do this computation. It's not extremely difficult. Then H C star to the D of U minus 1, T minus 2, W T B. So what is this? So this is U minus 1, T minus 1, W plus V to the D, multiplied by D, T to the D. U to the D, T to the D. This is of course equal to W plus U, T, V, D. Okay, so we can check in this example that is true. Okay, great. So let's see.
Well, what do you have when you wrote the sum? You wrote P twice. Maybe one of them's a Q.
Sorry. Yeah.
It's
So
small-
this is
small p.
Yeah. This is a small p. This is a big p. Oh, maybe I'll make it even bigger.
For the
Yeah.
purpose-
Sorry.
One is index filtration.
One is
and
taking
label
which filtration, the other is
Yeah.
label.
Sorry about that. Yeah, it's our standard to write like the ascending filtrations with the indices on the top.
Yeah.
Sorry. Yeah, that is. Yeah. I should fix that in the draft. Okay. Great. So I want to talk about a couple examples now where this is true, where you can actually check this, just to show that I'm not completely making this up. Let's see. So the plan now is to talk about some examples, so 2 classes of examples, and then after this I'll talk a little bit about how this relates to some conjectures about sort of Hodge numbers of Landau-Ginzburg models made by Katsarkov, Kontsevich, and Pantev. Okay. So maybe I'll go light on the examples, because I think maybe the more interesting thing is the Fauna stuff. Okay, so 2 examples. And so the first example is, let's let xn be the blowup of P2 in n less than or equal to 8 points in general position. So then E, there exists an anticanonical with the curve E inside of xn. And so xn minus E is a smooth curve, which we'll call un, is Calabi-Yau, and so it's actually the complement of an anticanonical divisor. And so this is the sort of example that I want to look at. So what is the mirror to such a thing? So I'm not going to explain in detail why this is the mirror, but maybe this is sort of clear. So the mirror is, let's see, so it's built as, so what do we do? So we take, so let's take a map, call everything f. Let's say, let's change it up a little, pi from Zn to P1. So let's let Zn be a rational elliptic surface with a cycle of 9 minus n rational curves as the fiber over infinity. I 9 minus n, the fiber. Okay. So this is, so we have this map, Zn to P1. Let's let Yn be Zn with pi, the fiber over infinity taken out. Okay, so I suspect this is the mirror. I mean, I don't think. I mean, there's of course justification in the sense that xn itself is mirrored to this pair. So if you take yn plus the restriction of pi to yn, that's going to be a Landau-Ginzburg model. It's going to be proper. So the fibers are going to be proper, and the this is going to be a log Calabi-Yau. So I mean, there's some justification for the fact that this is going to be mirror. Yeah. Yeah, I think I probably don't need to say too much
In
about
many
that.
different ways.
Yeah, I mean, there's.
I have a nice question. I don't know why n is less or equal than a.
Well.
Otherwise you don't have.
It's
So-
not a funnel otherwise.
Mhm.
It's not.
You want the blow-up to be a funnel.
Okay.
Yeah, and also if you see that if n is greater than 9 here, you can't
Yes,
really
okay.
play this game too well. Yeah, so I mean, if n is greater than 9, I don't think the mirror is supposed to be an algebraic variety. That's another.
Well, it depends on the configuration of the points, right?
Yeah.
So there is an interesting question when you take n points on an elliptic curve
Mhm.
and blow them up.
Yeah.
Then you'll be able to write a mirror.
Okay.
And then you can still ask this question.
Uh-huh.
But that's a different question. It's a quasi-funnel.
It's a quasi.
Fine.
Quasi-funnel.
Okay, quasi.
Okay, so given these two varieties, so I mean, so claim is that yn is mirror to un. Okay, and you can check that these H polynomials have sort of the right shape. So the H yn u v t w. This is equal to w plus u t squared, w squared plus u v squared t squared plus 9 minus n u t squared, and h un u v t w is equal to w squared plus u squared v t squared plus u v t squared plus 9 minus n u t squared. Okay, so you can check, unless I wrote these down incorrectly. So theorem is that h u n u inverse t 2 w t t squared is equal to h un u v t w. So this symmetry holds for this pair of mirror varieties.
But by the way, it should tautologically hold automatically for n equals 9. Is it
Yeah,
clear?
I should. Yeah, I'm sure the
I mean,
computation goes to n equals 9 as well.
Yeah, okay.
Yeah.
The formulas are the same. Is it
Yeah.
clear that the...
Yeah, I think so.
So what you're really saying is that you have the two terms, one involving n and the other not involving n, and when you do your flip of variables, the two terms go to each other.
Yeah, exactly.
Yeah, but polynomials have positive coefficients here and here. Yeah.
Yeah, so I mean, if n is equal to 9, we're good. Yeah. Okay, great. So this is a fairly easy to check example. I mean, it's not completely obvious, but it's not that hard. I'll use this one. And I'll just fairly briefly describe another example. That you can work out. It sort of turns out to be a fairly interesting combinatorial symmetry. So So another maybe 2. So let's let delta be a reflexive polytope. In dimension 3. Okay. Then let x delta be, I guess, a corresponding weak Fauna toric variety. Okay, so to any reflexive polytope, you can associate a Gorenstein-Fano toric variety. If you choose a triangulation of the faces, of the facets of this polytope, then this sort of gives you a Crepin resolution or a partial Crepin resolution. In this case, since it's dimension 3, there's actually a Crepin resolution, and so to any triangulation of the faces of delta, we get a weak Fauna toric variety. So we can construct hypothetical mirrors. I don't think anything at all has been proven in this case, which I'll call y delta. Well, okay, that's not really true at all. W delta. So what you do is you take sort of the general. So there's a general method of constructing mirrors to these things, but these mirrors don't have compact fibers. So what we need for this construction to be actually mirrored to x delta minus a smooth anticanonical divisor is that this be sort of W delta be a proper map to x delta minus B. So here B is smooth anticanonical. If we were to take take our anticanonical divisor to be the toric boundary divisor in here, then the mirror to that, x minus delta, so that just is a torus, so the mirror is a torus. So we want to do something more interesting, so we take a smooth anticanonical, and this requires that we compact by this thing. So this gives, oh, sorry. Yeah, no, it's no potential. Yeah, okay. Great. So we have some sort of hypothetical mirror, and I'll just describe, I guess in very little detail, that you can actually prove the same thing holds in this case. So the theorem is that the precise conjecture holds for x delta xv and y delta. Okay. Yeah, I didn't provide much detail here, but this is just like there's another several thousand cases that you can just prove. Okay. That's all good. Okay, so now I'll talk a little bit about so should I just be going for only 10 more minutes, 12 more minutes? Is that about it?
15.
15?
Plus.
Okay. So now I want to talk about the relationship between this and sort of topological mirror symmetry for Fauna varieties. So I'll explain what this is. So let's see. So I started by asking this question about how mirror symmetry relates Hodge theoretic information on log Clavier varieties to one another. So you have a mirror pair of log Claviers. How are the Hodge numbers related? You can, there's also mirror symmetry for Fauna varieties, and you can ask a similar question. So let's let x be Fauna. Its mirror is a Lino-Ginzburg model. It's called YW. Okay. So the question is how. So how is the Hodge theoretic data on X reflected in YW. Okay, so that's sort of the question. So we want to build some sort of Hodge theoretic data associated to Landau-Ginzburg models. So in Kensarkov, Kinsevich, and Pantev, they give a conjecture as to what this should be, and it goes as follows. So let's make the following assumptions about the Landau-Ginzburg model YW. So assume
The Fauna, do you think is A and B, or does that not matter too much?
in this case, no. I think you should probably be thinking of both as like there being an A component and a B component to both.
They both have both.
Yeah. So assume that so Y admits a compactification, a projective smooth compactification, which I'll call Z. There, and then there's a map. I'm also assuming that there exists a map. There exists a map F from Z to P1 such that, and this is stronger than the assumptions that Kensarkov, Kinsevich, and Pantev make, but this is sort of the situation that I want to be in, and assume that Y is actually equal to the complement of the fiber over infinity of F. So Z set minus F on infinity, and W is equal to F restricted to Y. Okay, so you have sort of a diagram here. Y maps to C, this is contained in Z, this goes to P1, and then here, I have this, well, I'll call this thing D infinity, and we have this goes to just okay, so we have sort of this diagram. So basically the point is I'm taking exactly the recipe that Kensarkov, Kinsevich, and Pantev consider, but I'm assuming that the map that you get is proper. Okay. Okay, so we define the F-adapted I-forms on Y. So the sheaf are on Z. F-adapted I-forms Z is the following. The sheaf forms W, so this is going to be a subsheaf of the sheaf of logarithmic I-forms on Z with poles, log poles at D infinity. So it's going to be a subsheaf of this, such that, this is the local condition, that when I take W and I wedge it with DF, this thing still has log poles. Okay, so it stays inside of this sheaf. So this is a subsheaf. It gives actually a subcomplex of the complex of logarithmic forms. And so we define, so then we'll denote this by Z I log D infinity. Yeah. Okay, so this is a collection of sheaves that sort of take into account both the logarithmic, both this divisor to infinity of Z and the function f. So then the definition is as follows. So FPQ of YW is the dimension of HQ Z coefficients in the sheaf. Okay. Sort of implicit in this notation is the fact that this doesn't depend on which compactification Z we chose, and that's something that they prove. Okay, so the conjecture is then again, here I'm going to be taking mirror symmetry as sort of a black box.
But here there's some kind of degeneration of spectral sequence, yeah, the story, yeah. So.
Yeah, I'll say a little bit about that. Not
okay.
probably enough, but a little bit, yeah. Because I want to talk about the other Hodge numbers that you guys defined. So the conjecture is that if X is mirror to YW, and I guess dimension of X, dimension of Y, D, then FPQ of YW is equal to HD minus PQ of X. Okay. So the same sort of symmetry holds for the Landau-Ginzburg models and their mirror faunas. I mean, so, yeah. Okay, so this is the conjecture. So what does this have to do with log Claviers? Well, I mean, if you have an anticanonical divisor, say reduced anticanonical divisor in X, you can actually build sort of a log Clavier just by taking the pair of X and that divisor. And if you take the complement of the divisor, you get a Clavier. So let's say a couple things. So if V containing X is anticanonical, expect, I'm saying this backwards, but I'll say it this way anyway because I suspect most of the audience understands this. We expect that X minus V is mirror to Y. So more precisely, what I should be saying here is that if I take X minus V, this is Clavier, then I have a mirror Clavier Y, and that when I put V back, what I end up doing is I end up adding a potential to Y. And this is sort of the thing you see corresponding to this compactification. Yeah, so this is what I should be saying, but that's what I wrote.
But Y is not necessarily log Clavier anymore.
Y is not necessarily log Clavier.
It can have poles of higher order. Yeah.
Okay, in all the examples that I want to look at, it'll be log Clavier.
Okay.
So, yeah, that's true. I mean, you can excise stuff that doesn't really change anything. The fiber. So if we do this process, not this way, but the other way that I explained, the fiber of W should be mirror to B. So the divisor that we took out should be mirror to the fiber of W. If we take this fiber to be maybe close to infinity or something. So there should be really like 3 different forms of mirror symmetry going on here. You should have mirror symmetry for log Claviers, mirror symmetry for, I guess, the fiber here and V. So if we assume that V is compact and smooth, then we expect the fiber to be compact and smooth as well. So we should have mirror symmetry for Claviers, mirror symmetry for log Claviers, and mirror symmetry for Faunas. Fauna-Landau-Ginzburg types. Okay. So let's see. So here's the theorem. So if we assume that these things are true, and we assume part of this conjecture on the board over there, the precise conjecture, then we can actually recover this conjecture of Sarkov, Kontsevich, and Pantev. So theorem. Let's use myself with Udmil, Vincent Puchalkowski. So let's let, this is a fairly vague theorem, let X be a variety be a smooth anticanonical divisor. And then let U be x minus d, so the complement, and let YW be a Landau mean squared model. Such that W is proper. So the fibers are compact and, I guess, generally smooth. I'm assuming Y is smooth. And let's let W is bad. So V be a smooth fiber of W. Okay. And assume the following two things. A, HPQ of U is equal to HD minus PQ of Y for all PQ. Okay, D is again the dimension of X and Y. So this is assuming sort of the first thing that I claim, that there's this sort of Hodge number flipping for just these open quad-Yaos. And let's assume that we actually have the expected duality for V and D. Okay. So that HPQ of D is equal to HD minus 1 minus PQ of V for all PQ. Let's assume that this is true. So then, let's call this conjecture star. So then, conjecture star, is equivalent to the fact that H Y U minus 1 T minus 2 W V T 1 is equal to H U 1 T W. So this is exactly the conjecture over there, where I'm just setting W equal to
W?
sorry.
Oh, then right hand side also should put 1. W?
Yeah.
I take V equal to 1.
Yeah, V equals 1. Mm-hmm. So this is equivalent to V equals 1. So assuming things about the fibers that they're actually mirror to the anticanonical that you took out, and assuming that the total spaces have this sort of rough duality, then this conjecture of KKP is equivalent to this duality.
So it means that F you can calculate through some usual Hodge theory, yeah?
Yeah, exactly. I mean, so that was something that, essentially you can pull out of your paper, but I wrote down some other
So Mochizuki worked on this F numbers, F,
You might have. I don't know.
No, Takuro Mochizuki, yeah, he had a couple of papers about this stuff, yeah.
Okay, I don't know. I think a student of his, I know one paper.
Yeah, a student of his. It was.
Yeah.
So?
Yeah, it was a student. It wasn't.
No, he himself had
Yeah.
I don't know. I mean,
Yeah, okay,
student
maybe I don't
Shimoda
know
has got a really nice paper on this. Yeah. Okay, so this is the first question.
Would you write the hypothesis X be a what?
Smooth variety.
Oh, smooth.
Yeah. Okay, so this is sort of general stuff. And so, do I have time to explain one more theorem, or should I end here?
You have 2 minutes.
2 minutes. Okay. Well, I'll give an abridged version of this other theorem. I won't explain what these invariants are, but I'll sort of give a vague explanation of what they are. So, KKP, Katsarkov, Considered, and Fantov also define numbers HPQ, YW, coming from the monodromy of the relative cohomology. From certain monodromy filtration. And I guess if I write it this way, maybe it's not so unclear what this is. Sort of the expected thing you get from varying V around infinity. And so they conjecture, if I had more time, I'd explain why this conjecture should be true, that if X is Fauna, and a YW is its mirror, that FPQ YW is equal to HPQ. So this is just something to do with, you know, restrictions on the structure of sort of the cohomology of these Landau-Ginzburg mirrors to Fauna varieties. So the theorem that we prove is that if we assume that we have a Fano, and we assume that part of these conjectures over here hold, then we actually get this equality. So let's say this precisely, and that'll be the end of my talk. So the theorem is that if, so let X be Fano, D be smooth, anti-canonical, X. Again, let U be X minus D. So, and let's let YW be a Landau-Ginzburg model so that W is proper. So it's the same thing as I was assuming up here. So assumptions are the same as in this previous theorem. And assume, that so HY U minus 1 T minus 2 W T 1. That's not the same. Oh. Sorry. So that was this. This is equal to H U. D, D, W. So let's assume. Sorry, this was wrong. I wrote this down wrong. So this is exactly what was before. Then HPQ YW is equal to FPQ YW. Yeah. Okay. So if it's Fauna, if this is true, so half of this conjecture over here is true, then we have that the HPQs are equal to the FPQs. Okay, so that's it.
Thank you.
Can you remember, just at some point, I remember Lund contacted us and said that they found some counterexample.
But this was with the IPQ ones coming from
It's the
advantages.
definition of the ones coming from the limited mixed order structure.
Okay. So it's some
And
sort of one.
in fact, this is the thing that corrects it.
So now everything's fine. Yeah.
Sort of. Well, yeah.
Is there like a question to do afterwards to treat the case of non-smooth divisor?
Yeah, that still exists. I mean, there's and that's a really interesting question. I mean, it's a bit of a rabbit hole you can go down if you want. But.
Yeah, it is a serious question. One needs to look at examples before we can even formulate.
I've done a couple computations with non-smooth divisors, and it's not pretty, but you can do it.
Thanks.